recorded the session. So thanks for today's session. So today we're going to talk about another new data structure. Okay, this is also one of the most important data structure in the programming world. Okay, and earlier we learned array, we learned linked list, we learned stack, we learned queue. Okay, they are all linear data structure. Okay, linear data structure, which means it's like a chain, right? And most of the data structure were implemented by the what? Linked node, right? We create a node and node had a next reference, right? And then we link node one by one. Okay, but it's linear. Okay, there's only one dimension, one chain. Okay, now today we're talking about tree, a little bit different because you can imagine tree has different branch, right? So that is not linear anymore. Okay, we call that hierarchy data structure. Okay, it can have different dimension, different chain of the node. Okay, but let's take a look at it. So why we call that tree? Because in our daily life we see the tree plant, right? So we can see it have a trunk, and then trunk have a branch, branch have a smaller branch, right? So it expand, it can expand, right? So that's a tree in our life. So similarly, right, when we mapping such kind of structure to the programming world, right, you can imagine some structure like this. Okay, it has root, and then it has branch, right? If you learn HTML before, right, HTML had the root tag, right? HTML, and then under the root tag, it can contain multiple child tag, right? Like head, like body, right? And then in each child tag, I can have another child tag. Okay, so that is also another example, right, of tree structure. Okay, so simplify all those scenarios in a simple way. How we understand the tree in the context of a data structure is something like that. Okay, 1, 2, 3, 4, 5, 6, 7, 8. They are the values stored in the tree data structure. Okay, we can see the tree is starting from top. Okay, so that is a little bit different from the normal tree, right? We have a root at the bottom and then expand upward, right? But in the data structure tree, we normally to imagine it starting the root is starting from the top. Okay, because that's will be easy to imagine, right? So it's starting from the top node, okay, and then expand the tree, okay, and the tree can be infinite, right? Because I can expand it on different levels. Okay, so that is way how we understand the tree, the structure. Okay, so let's move to the next slide. Tree structure in life, right? So we have lots of different examples about the tree structure in life. Okay, I just give you two examples. The first example is about the family tree. Okay, family tree. So we have grandfather, grandmother right on the top. This something like the root of the whole tree, right? And then when they have their child, okay, they have the father, mother, uncle, auntie. Okay, so they expand. It's something like expand the tree, right? And then for their child node, right? For their child node, father, mother can have 3 children, right? And uncle, auntie have 2 more children, but they are under different branch. Okay, so you can see a tree starting from top, expand one level and expand another level, and could be expanded infinitely, right, in the future. Okay, so that is one of the examples about the tree structure in our life. I give you a second example about tree structure in our life is most of you guys are playing games, right? In the games, when you have a character, okay, you upgrade your, what's that called, skills, right? Or different, technology skills. and based on the different level you are, right, you may can expand the skills or expand equipment you can buy or you can own, right? So such kind of things we also call that tree, okay, because it has the root, okay, and root can expand, okay, to different child node, okay, and the child node can expand to another generation of the child node, okay. So from top expand downwards, okay. So that's another type of the example of the tree structure, okay. So now let's take a look at what the parts do we have in the tree, okay. So that is a structure of a tree. So as I said, when it's a tree, okay, it's starting from a root, okay. The root is the most the topmost element or topmost node you have, okay. Just like the head, right? The head we have it in the linked list, right? You create a linked list, or I give you a linked list. I usually just give you head, because why? Because starting from head, you can access all the nodes in the list. Okay, so similarly here, for a tree, I give you the root node. Okay, once you have the root node, you can expand and visit all the children nodes. Okay, I got the following, right? So we can see here, right? Node A is root. That's easy to understand, right? Because the whole tree is starting from A. Okay, and then A has two, what we call that? Has two child node. Okay, child node, because to A, B, and C, right? They are the nodes under A, so they are called that child node. Okay, and then you may ask me, hey, why in the diagram it's labeled as a parent node? Because this parent node is related to whom? To B's child node, D, E, F. Okay, seems you can see the whole tree, right? You can see the whole diagram as one tree, but within this one tree, it actually has different subtree. You see this as a triangle, right? So this is basically a small part of the whole tree, and we can also call that subtree. Okay, so in this subtree, in the context of this subtree, you can say, hey, B is the root node, right? And also it is a parent node of whom? Of his child node, which is D, E, F. Okay, so that's a relative, term, right? Parent node is a term, right, related to his own child node, right? And child node is a relative term to his parent node. Okay, so we have root, right? And we can have multiple subtree in the whole big tree. And then in each tree, we can have parent node, child node, right? Also, if you look at the B and C, okay, B and C, they are child node of whom? Julian, node B and C, they are child node of whom? Julian?
Well, I can't see.
You cannot see my screen?
I mean, I don't see the C part.
How can I don't see the C part? You cannot see my whole screen.
Yes, the camera thing is blocking the way.
Hmm. What about others? How about now?
Huh?
Are you able to see my whole screen?
Now I can see.
Okay. Did you get my question?
I didn't get it.
My question is, do you see the tree here?
Yes?
Okay. A is the root, right? So I'm asking you, B and C, okay, these two nodes are the child nodes of whom?
Yes?
A, right? Okay.
Yeah.
So B and C, they're the child node of A, right? And
Yeah.
vice versa, right? A is parent node of B and C. Okay, so that's easy to understand, right? And
Yeah.
further, what we call between B and C, they are what? They are siblings. That's easy to understand, right? Okay, that's easy to understand, right? If you have more than one kid at home, you have a brother, you have a sister, right, Louis? You and your sister is called siblings. Okay? Louis, are you following? Hello, Louis. Why you and your sister is called sibling? Because you are all child node of the same parent node. Okay? That's clear, right? You cannot like a sibling be any other people, right? Because it has to be from the same parent node. It's easy to understand, right? Okay, so now let's take a look at another concept called, okay, here, every line between the node, like A, C, A, B, right? The line we call age, okay, just like age in any like demographic, in the math, right? You have the diagram, right? You have the dot and you have age. That's it. And then we can see another type of node, okay? We call it leaf node. That anyone can make a explanation or guess what kind of node we call that leaf node. Aston, in a tree, what kind of node we can call it leaf node? Hello, Aston. Hello? You guys there? It's my connection issue.
No, I hear him in a weird way.
I know. Jeffrey.
I think he's talking in slow motion.
Why does it sound like your voice was auto-tuned?
Okay. Aston? Hello, Aston, you there?
Yeah, I'm here.
Okay, what happened to your internet?
I don't know. My computer freaked out.
Okay, did you get my question?
No.
Okay, are you looking at my screen? Are you able to see my screen?
Yeah.
Okay. In the screen, okay,
No.
we have the root, we have the parent node, we have a child node, right? And here we have another kind of node called the leaf node. Okay? Leaf node. Node G is leaf node. Okay? So my question is, what kind of node we can call that leaf node? Aston, by looking at this diagram.
Child node?
Child node, okay, then B is also child node of A, right? E is also child node of B, right? But they're not leaf node. Think about a tree. You have a tree, you have different branch, and on the branch we have a leaf. So a node we call it leaf node, which means what? Which means that's the end. What end means? Which means it doesn't have any child node. Okay, clear? So for those nodes in a tree who don't have child nodes, we call them leaf node. Okay, so Victor, in this tree, okay, who are leaf nodes? Victor?
Well, I couldn't hear. My audio was lagging.
Did you get my question? My question is, in this diagram, okay, which nodes are leaf node?
G.
G? Yes, you're right. Anything else? Any else?
No.
But listen to me, right? A leaf node, which means a node doesn't have any child nodes. I can tell you that the more leaf nodes here. It just didn't label it out, right?
Oh,
I needed
HF.
HF.
Wait,
G.
no. Wait, it's H and F.
HF is correct. One more.
And D.
D. Very good. We can see here D, H, F, and G. And they are the nodes, but they don't have child nodes below them. So these nodes are called leaf nodes. Okay? Louis, are you following? Okay? So A, B, C, and E here, we cannot call them leaf node because they have at least one child node. Clear? I think I explained clearly, right? Okay. So look at this diagram, right? Similarly, we have a root. Okay, we have a parent node, child node. We have a subtree. We have a leaf node, and then we have sibling. And if on the right side, you can see level 0, level 1, level 2, level 3. What does it mean? Because as I said, right, from the root of the tree, it can expand. Just like, you know, the family tree. You can have multiple generations, right? You can have multiple generations, but the same generation. So for example, you, right, and the kids of your uncle, you guys are in the same generation. Okay? So here we can also in the level to indicate which generation you are. The root, level 0. Level 1, which means the first generation under root. Okay? Level 2 means what? The second generation of root. Okay, so level 3, level 4. Okay. Does it understand, right, Julian?
Huh?
You understand what I'm talking about, right?
Yes.
Level. What's the meaning of level? Means what? Level is the generation, right, of the
Yeah.
child below the root node.
To the
Okay.
child, to the parent, to the root.
Say it again.
To the child, to the parent, to the root.
Yeah. Okay. So now let me ask you a question. Julian, what is the level of node J?
Huh?
What the level of node J?
Root.
Hmm?
Root.
I said J, not A.
I didn't quite hear that. All I heard was something about J.
J, yeah, J for Jack, right? Node J, do you see node J? What's the level of node J?
Child.
No, I'm asking you level.
Oh. Level 3.
Level 3. Okay, now I'm asking you, node J is the child node of which node? Node J is the child node of which node? Julian.
E.
Yeah. Very good. Jeffrey. Jeffrey. You there, Jeffrey? Hello? Jeffrey. I see you on mute, but I cannot hear you. Okay, how about Louis? Are you there? Hello, Louis? That's whose voice? I think, Jeffrey, you have an internet connection problem. I don't know which one, you or Louis. Louis, you there? Hello,
yes,
Jeffrey?
I'm here.
Jeffrey?
One thing right now.
No, it's still not good, okay?
Yeah, I thought my connection was bad, but yeah.
Okay, Louis, I can hear you. Can you hear me clearly?
Yes.
Okay, answer my question. How many child nodes does node D has?
3. I'm liking.
Okay,
Me.
okay, I think his connection is not good. Louis, answer my question. How many child nodes do we have for the node D?
3.
What's 3?
D, E, and F.
I said how many child node of node D? Where is node D? Node D is here, right?
B or D?
D. Sorry, D. Dog.
What?
D
B,
for dog.
D, or E?
I said node D. D for dog. I'm pointing to the node D here. Okay?
Oh, duck?
For node D, how many
Oh,
child
2.
nodes? Okay, what are they?
H and I.
H and I. Okay, then how many child nodes for node B? B for boy.
D and E.
D and E. Okay, and who is the parent? Who is the parent node of node F? Louis. Node F. Who is the parent node of node F?
C.
C. Okay. How many leaf nodes do we have in this tree? Louis, how many leaf nodes do we have in this tree? Louis? Louis, are you there?
4.
How many child nodes do we have in this tree?
Seven.
Okay, Louis, do you get him a question? How many leaf nodes do we have in this tree?
Hear me?
4.
What are they?
Or D, E, F, and G.
You guys hear me?
No, Jeffrey.
E, E, F, G? No, that's not correct. Aston, you there?
Yeah.
In this tree, how many leaf nodes do we have?
1, 2, 5.
5. What are they?
H, I, J, F, and G.
Okay, very good. Okay, Louis, you give point. Right? H, I, J, F, G, because they are the nodes who doesn't have any child nodes, no matter which level it is, okay? Okay, no matter which level it is, right? It's something like the leaf, right? Leaf can have existing in different branches of the tree, right? So that's the same understanding. Okay, very good. So you guys have a basic understanding of the tree. So let's continue. Okay. In the programming data structure, right, we have different type of tree, okay, based on the, some character or some features of the tree. Okay, we can say it's a generic tree. Generic tree, the most generic tree, right? You can have you have one root node, and then you can have different, different number of the child nodes. Okay, different number of the child nodes. Okay, so, and we also have a binary tree, binary search tree, okay, AVL tree, red band tree, whatever, okay. So these are the different types of tree, and we may talking about in the future, but not right now, okay. So if you wanted to learn some of that, right, I can put this link, okay, in our class information, which you can just take a look at, okay. 8 useful tree data structures worth knowing, okay. And then today we're gonna focus on one of the classic type. It's called a binary tree. Okay, does anyone know what's meaning of binary? Connor, do you know what is binary mean?
Does it mean that it can only have two children?
Yes, you're right. Okay, binary. Okay, binary is very fundamental stuff in programming. Because why? If you know, the whole computer system is invented based on the binary number. Okay, binary number. I think you guys also learned in the math, right? 1 0, 1 0 0 1 1 0 0 1. We call that binary number because it can only have 2 different values, 1 or 0. Okay, so all the computer works is based on 1 and 0, if you understand. Okay, no matter what you having in the computer, okay, when the computer is executed or processing on the hardware only understand 1 0 1 0 1 0. Okay, so that's the fundamental stuff of the whole computer. Okay, so the same term binary we also need here, right? As Connor just mentioned, which means if a tree, for every node in the tree has at most, okay, at most, okay, at most 2 child nodes. Okay, we call the tree is binary tree. Okay, so it is a tree. It follows all the property of the tree, like what? Had the root, okay, had a parent-child nodes, right? And nodes is connected by edge, okay? Okay. So a binary tree has its own character, which for every node in the tree, right, had at most 2 child nodes, okay? But try to understand at most means what? Child nodes bigger or equals to 0, but smaller or equals to 2. Which means for every node, it can have 0 child nodes, so which means he is a leaf node. It can have 1 child node, okay? It can have 2 child nodes, okay? So that is at most 2 child nodes mean, right? And Because I have only 2 child nodes. So normally we classify them as a left node or left child and right child. Okay. So for example, in this tree, okay, Victor, what is root node?
I'm not sure. I don't know this one.
What's meaning of the root node? Root. Everything is starting from that. So here, which is root node? Ashton.
P.
Okay, P is the root node. How many child nodes does P have?
2.
Q and R, right? How many
Yeah.
child nodes does Q have?
2.
And B. How many child nodes does A have?
1.
Okay. So as you can see, right, for every node, okay, in this tree, it has at most 2 child nodes. So we can call the whole tree as binary tree. Okay, understand? Victor, you understand that?
Yeah.
Okay, now let's continue. Let me ask you, by looking at the following tree, you can tell me, okay, if it's a binary tree or not, okay? Jeffrey, are you able to speak now? Is the connection good now? Jeffrey? Okay, Louis, is this tree a binary tree? Louis? Julian,
Huh?
is this tree a binary tree?
No.
Why?
Because it has more than 2 lines of nodes.
Which node? Huh? Which node break the rule?
10?
I'm asking you, which node break the rule? And you said it's not a binary tree. Huh?
I don't know.
Now how you can tell it's not a binary tree? And I think I explained clearly, right? What are the type of the binary tree, right? Every node has at most 2 nodes, right? So then take a look at the tree and tell me, does it meet the requirement? Julian, look at each node. Huh?
2?
Huh? Victor,
Yeah.
it's a binary tree.
What?
It's a binary tree.
I can't hear you.
I mean, is it a binary tree?
Yes.
Okay, so does every node in this tree has at most 2 child nodes? You say yes, right?
Wait, yeah.
Are you sure?
I
How
mean,
about
no.
node 7?
Wait, what?
Node 7. How many child nodes does node 7 have?
3.
Okay, so you did binary tree.
No.
Okay. It's straightforward, okay? Next one, Julian. You did a binary tree.
Yes.
Okay, because every node here at most two nodes, right?
Yes.
Okay. Victor, you did binary tree.
Yes.
Okay. You can have like 0 child nodes or 1 child nodes or 2 child nodes. Okay. So this tree is meet the requirements. Okay. Aston, you did binary tree.
Yes.
Okay. What about this, Aston? You did binary tree.
Yes.
Okay. Okay, you guys understand the concept, right? Every node had most 2 child nodes. Okay. So look at the last one. The last one is actually it's similar or equals to a linked list, right? If you noticed, because linked list is what? Linked list is a linear data structure, which means it can only point to one node, right? So even, right, it is a tree, but if every node in the tree has only one node, that is equals to linked list, right? Okay, since we understand the binary tree, so now, or another thing, right? Why tree? Okay, why we said tree is the most important, data structure in the programming. Okay, different from the linear data structure. Okay, because in our daily life, the lots of information we have to store in the hierarchy. Okay, structure. Okay, so that's the reason why we have the tree. And the second point is, which I'm gonna explain like in the future, is about when we run the different algorithm. Okay, we said that we're gonna learn the structure and we're gonna learn algorithm, right? So in the turn of algorithm, tree is usually provide a pretty good speed to do search. Okay, that is based on some features of the tree. Okay, similarly, because a tree is also consists of nodes, right? The nodes means you can either do insertion or deletion, right? It's not index based. Okay, it's not continuous memory location. So if it's linked by the nodes, it is usually fast to insert or delete. And also because it's linked by nodes, which means there's no upper limit for the nodes. You can link as many as nodes you want. Okay, so that is all the advantage of the tree data structure. Okay, so now today's assignment is about create your own binary tree. Okay, own binary tree. Okay, and here we're gonna also using the node, okay, as our item class. But differently, the difference, right, between this node and the other nodes we used before. Yes, what's the difference? Louis, you there? Hello, Louis.
Yes, I'm still laggy. I can't.
By looking at this node class, can you tell me what's the difference from the node we write before?
The self, the left, right, and everything.
First of all, how many properties do we have for this node class?
3.
Okay, what are they?
Left, right, veil.
Okay, left, right, val. Val means value, right? It's just abbreviation of value. So early in the linked list, in the stack, in the queue, or where you need node, right? We only have value and next, right? Next is the reference what pointing to the next node. Okay. Here we said it's binary tree, and we have a left child and a right child. So we basically needed two references. And to distinguish them, okay, we make it be left and right. So they are similar as next reference. They're just pointing to the child node or another node, right? Another node. Okay, so that is how we construct the node class, right? So now let's create together. Okay, so we're gonna create a class node. Okay, and again we have a def init function, right? Self. How many props do we have here? 3, right? So we need to have. Oh, wait a second. We don't need to pass it left and right because why? Because they are not mandatory when I initialize the node, right? I just pass in value. Okay, and here self dot left. Okay, let me set the value first, right? Self dot value, you can set a value directly. Okay, that is taking the prost value as the date value of my whole node, right? As well as I need a left node. Okay, it's initialized as a num. Okay, because I'm just one node. I don't have any child node as a beginning. It's defined as a node. None. And we have right node. That's it. I create a node. I create node for my tree. Okay, we can also call that tree node. Okay. Now, next, what are we gonna create? We're gonna create our own binary tree. Again, it's a binary tree. Okay. So we have a node. Hey, did you find we're not having any tree class, right? If you remember in our early task, right? We have node class, but as well as we have other class like linked list, like stack, like queue. Okay, but here when we talk about tree, we only have node class. Because why? Because the whole tree is starting from a root node. Okay, so I only need to know the root node. Then I can able to access the whole tree. Okay, so if we look at the code here, right? I have node class already. Now I can create my root node. So usually we have root node, right? I create a root node. Okay, again, the root is also a normal node, right? There's no difference. Node said 10 or 1, whatever, right? 1. So you can say I create a tree, but the tree only have one node. Then how about I continue to create nodes and add to it? Okay, let's try that, right? You said the left node, node 2, right node, node 3. Okay, so we have created 2 nodes and which we're going to use that as child nodes. How can we connect that? Right, in the linked list, how we connect a node into the linked list? We set next equals to a new node. Same thing here. How we create relation between the parent node and child nodes by setting the left and the right reference. Okay, so root dot what? Left equals to node. No, right? I already created node, right? The left node. and root dot right equals to right node. Okay, so I have a left node and right node. I have a tree, right? If we go back to the slides, I create root. Okay, and if you imagine, right, how the tree will look like, it will look like this, right? I have a node 1, and it has 2 child nodes, right? Num, num. Okay, and then I have a root dot left. Make the left pointing to another node 2, and make the right pointing to another node 3. So if you imagine the tree will look like this, right? I have a root 1, and it has 2 child nodes, 2 and 3. And a while for 2 and node 2 and node 3, they don't have any child nodes, right? No. Okay, so how can I add another level of the child node to my first generation of child nodes? What do you mean? Here, I wanted to add node 4, make it be left node of my node 2. How can I do that? Okay, in my way, that's easy, because I already create a relationship between node 1 and node 2. Okay, I have a variable here, right? Left node. I wanted to add another node, right? Be the left node of my node 2. What can I do? Right? Left node left equals to node 4. That's the one way. Which means what? Which means I set the left node to the parent node directly. Okay? Jeffrey, Louis, are you guys listening? Okay? I set the left node to the parent node directly, but there's another way, just like how I'm showing here in the slides. I can always, starting from the root, to find the node where I want to make the changes, right? The root is 1. Root left is node 2, right? I want to set the left child node of node 2. You can say root left equals to new node, right? So there's another way. So suppose I make the changes for the right, which will be left node, not left node. I said starting from the root. Root starts right equals to node 5. Okay, so how it will look like? It probably look like this, right? So if it will probably like that, right? 1, 2, 3, right? 4, 5. Okay, so imagine that the line, okay, that the line between the parent node and child node, right? So look at my code. 1 is the root node. It has left node 2, right node 3, okay? And then for the left node, which is 2, I set the node 4 as his left node, right? His left node. And then I set what? You can always start from root to set the child node, right? I did it from the right node, right? Though I know the node 3, the right node, but I starting from root. So I'm using root dot right with 3 and dot right and make it equals to node 5. That's the same result, right? That's the same result. But you just need to be careful about the left and right node. Okay, left and right can point into none, but as well as can point into a node. If I point to a node, you can always set the next child node of that existing node. Okay, Aston, are you following?
Yeah.
Okay. So that's it. Quite simple, right? You just need to create a one node class, and then you create a new object of the node, right? By giving a value. And then you can create nodes and set as a left, the right, okay, of the node. Okay. And now let's talking about how we can print out the whole tree. Okay. So we know, like, when in the linked list, right? We also create a way to print every value of every node in the linked list, right? What we do is, we are starting from the head and the while loop, and a while basically looping every node in the list to the last one, and print out or concatenate the value, right, from the list. But the tree, the problem of the tree, or not the problem, the fact of the tree is it's not linear. Okay, it's not linear. You cannot using a while loop, right, to loop every item of a non-linear data structure. So how can we do that? So here we can introduce another very important concept in programming. It's called recursive function. Recursive function. Okay, Connor, do you know what the recursive function mean?
No.
Okay, recursive function, which means I call myself. Okay, look at this example. I create a print tree function, and inside of my function, I call myself. Why? Because we know the tree consists subtree. The subtree consists another subtree, right? So it can be infinite. How to say that? Infinite generation, infinite run. Okay, there's no way for me to understand the beginning and the ending. Okay, because normally when we do the loop, we said, okay, starting from 1 to 10, we know the beginning, we know the ending. Okay, when we are doing the while loop, okay, we said based on some condition, we know when the next node equals to none, then we start the while loop. But not easy for the tree, because we don't know how many nodes. We cannot like, hey, counted how many nodes in the tree and then say, like, from 0 to 10. Okay, because it's not linear. So here we are using a concept called recursive function, which means every how to say, it can be used in lots of different scenarios in the programming, in the problem solving, right? But you can keep it in mind when we're going to use recursive. It's normally the whole big problem consists or can be divided, can be apart into similar small problem. Okay, but that small problem can again be divided, right, into similar structure of smaller problem. So in this case, we can use recursive. Okay, because for each sub or small problem, we're using the same way to handle that. So look at the print function. Okay, I call the print function print tree function. Okay, that is a function belongs to the node. Okay, And I'm checking, hey, if self.left, Aston, what is the if condition doing here? If self.left, what does it mean?
It's checking if has a child function, as a child node.
You're right. It's checking. Do I have a left node? Okay. So I have left child node. And if I have, what I'm doing, I'm just call my left node dot print tree. Why? Because my left node is also a subtree. It's also a tree. Okay. And then you call your left child, and then what? Print self.data. Self-data is easy to understand, right? I just print out my value. I print out my value. So imagine you have a tree, okay? You give the node, the root node. First, you print the left tree, then you print yourself, and then you print your right tree, right? This is how I do it, right? If self the left existing, I just print the left tree, and then I print myself. Okay, I print myself, and then I print my right node if it is existing, right? I can only call the print tree on my left on my child node if it is existing. Otherwise, I'm gonna get what? I'm gonna get non-type error. That's very important. Okay. So let's try to implement that, right? Okay. Yeah, so I create the tree. So I want to print out, right? How I can print out. I said I can define a function called print tree. Okay. So I'm gonna first check from left myself, right? Okay. If self dot left, if my left child existing, I do what? I do self dot left dot print tree. Why I can call this tree? Because what? Because my left is also a node, right? That's the reason why I can call the node dot print tree, right? Every node has a print tree function. It's basically print my left subtree. And then I said, okay, after print my left subtree, okay, I print my own value in the middle. Okay. And also I can check if my right existing, same, I'm gonna set the right of print tree. That's it. So now let's take a look at that, right? Okay, so I have a root node. Now what happened here is I said I will not call print, okay? I can say why. Why I cannot call that? I call this. What I can get? My memory location. Yeah. I need to call the function. Root dot print tree. Okay, I have a function called print tree function. Now I run this. I got a 1, right? There's only one node in my tree right now. It's 1. Do I have left child? No. Right? Here, I don't have left child yet. Do I have right child? No. I only have myself. So then what happened if I know? Right? Here I didn't add a child node yet, right? Here, if I print out, okay, you know what? Make this 213. 213. From left, myself, and right. Okay, 2, 1, 3. What happened after adding 4 and 5? Remember, right? That is my tree will look like. Okay, that my tree will look like. So if I call the print tree function at that moment, right? Aston, what you're gonna see in the console? What's the order of the value you're gonna see in the console?
4, 2, 1, 3, 5.
Okay, very good. Okay, because it has print the most left node first, right? The most left node first. Okay, it's interesting, right? Let's try this. Add a more complexity. 1, 2. Okay, added 2. Set it. Okay. So I said left node, right? Let's add it right. It's a node 6. Okay, what's me? My left node had the right called node 6. Okay. Like that, right? Node 6. I make it separate. This will be easy to see. Okay. And then I wanted to make that, hey, root the right, which is node 3, the left. Okay. So the left of the node 3 can call node 7. Now I'm asking you, if I print the tree, what will be the order? Julian, you want to try?
Huh?
If I call the print tree function for this tree, okay, 1, 2, 3, 4, 6, 7, 5, what will be the output order in the console?
1, 2, 3, 4, 6, 7, 5.
1, 2, 3, 4, 6, 7, 5. No, it's not correct. Okay.
1, 2, 4, 6, 3, 7, 5.
1, 2, 4, 6, 3, 7, 5.
I don't know,
it's-
I'm guessing.
No. Victor, do you want to try? Think about that, right? It should print most left node first, and then myself, and then right node. Victor, what order you think is going to print out?
I think it would be 7, 4, 6, 5.
7 first. 7, 4, 3, 6, 5, 2, 1. No, that's not true. Aston?
4, 2, 6, 1, 7, 3, 5.
1, 7, 3, 5. Okay, let's work at it, right? 4, 2, 6, 1, 7, 3, 5. That's correct. Why? Think about that, right? Because I'm calling the root of print tree, so it's starting from the root. Okay? And when it's coming root node, right? We're gonna first take a look at the left subtree, which is 2, 4, 6. But when it comes to the left subtree, we looking for the left of that subtree also. So 4 will be printed out first. And then, does 4 have any child node? No, I don't have. So then this part is done. 4, and I can print out myself. 2, and then print out the right node. The right node has child node? No. Right? So then this subtree is done. And once this subtree is done, I'm going to print out myself, 1. Okay? So the order will be 4, 2, 6, 1, right? And on the right side, 3, 7, 5. This subtree, which one going to print out first? 7, because that's the left part, right? 7, myself, last one is 5. Okay, guys, get that? Very good. Okay, so we introduce a recursive function, right? How we can print out the tree. And let's make it more readable. I try to print out this, right? Let's try to do that, right? So right now, we print out the tree. Okay, we print out node every time. Okay, so how about not print on the node, and let's try to return okay, return this. Okay. No, our okay. Today I'm not talking about this. Okay. I'm gonna finish one slide here. Okay. Let's continue talking about this one. Okay. There's another special type. Okay. In the binary tree, we call a binary search tree. The abbreviation is BST. Okay. If you look at the diagram, it's clearly explained to you what type of binary tree is a binary search tree. Okay. When the left node value smaller or equal to the middle node value and smaller or equal to right node value, it's called binary search tree. Left equals smaller or equal to parent and smaller or equal to right. Okay, look at the tree example. On the root 56. Here's okay, so in this tree, right, the BST tree, which means its left node, its left node is smaller or equal to the parent node, and also the parent node is more equal to the right node. Okay, look at here, the root node is 56. He has a left node is 30, which is smaller than himself. And meanwhile, his right node is 70. Okay, so which is bigger than himself, right? And look at 30. The 30 node, okay, his left node is 22, which is smaller than himself, and his right node is 40, bigger than himself. Okay, so that is a typical feature of BST tree. Why we call that binary search tree specifically? Because this kind of data structure is easy for us to search an item. Okay, and that is the most, right? It's the fastest data structure for search. Why I say that? You can imagine if I give you a list, I'm asking what's the smallest number, or no, not smallest number, right? I give you a list and I give you a given number. Okay, I said I give you a list. Hey, find me what is the position or what do you have the value like 16, for example, right? 16. Do you have a value 16 in your list? In this case, what we're going to do? If I give you a linked list, I'm asking you, do you have number 16 in your list? The only way we can do that is looping from the head. Right? Looping from the head and check one by one. Check every node value. Are they equals to are they equals to value 16? That's the only way. So what's the best case? 16, the first node. I can just check one node. You got the answer. But what's the worst case? The worst case is the 16 the last node. So which means what? Which means you have to loop the entire list and find out that the list has the 16 or not. Okay. So imagine if you have the data is stored in the binary tree structure, right? The data is stored in a binary tree structure. How are you going to do the searching? Okay, I give the root node 56. Okay, so we know 16 is smaller than 56. Right, in the BST, then I know, oh, I just need to look at his left child or his left nodes. Am I right? Because we know BST has a feature left smaller than or equals to the middle, right? And right is bigger. So if I know, oh, the number I'm looking for 16 is smaller than 56, so I only care about the left part. So which means it's reduced the scope of my search. Right? And then come to the next level, which is 30. Oh, I look at 30. Oh, 16 is smaller than 30. So what does it mean? I just need to care about the left side. Okay? I again narrow down the searching scope. 22, smaller than 22, look at the left only. 11, let's count 11. We know 16 is bigger than 11, so I need here look at the right part. Okay, when I come to the right part and I'm checking, hey, is the value equals to 16? Yes, equals 16, I found 16. So in the BST structure, when you do the searching, it's most fast because it's always and dump another part of the number because of the BST feature. So that is the fast way, right? This tree structure is the fastest way to find out an item. Okay, and also repeat the feature of the BST again, right? Every left node is smaller or equal to parent one, which is the middle one also, right? And the right side node is always bigger or equal to the middle. Okay, so that's about that. Today, we introduce the tree structure, right? And we also explain details of binary tree, how to create our own binary tree. Okay, and last, we also introduce very important search, right? Friendly data structure called BST, binary search tree. Okay. And the next class, we're gonna speak more or give you more example about BST. Okay, and today's assignment is mainly gonna asking you to create your own node and own tree, construct your own tree, right? Okay, so do we have any question? Any question for today's class? Okay, if no more question, I think that's the end of the class. Okay, I'm gonna upload the assignment and the video tonight. Make sure you guys go to the video if you have any questions. Otherwise, try to finish your assignment as soon as possible. Okay? Don't wait till next Monday. Okay, Jeffrey, Louis, Victor. Okay, I have to remind you again. Okay, I hope you can guys finish the assignment as soon as possible. Don't wait. Okay. Okay, so that's it. Thank you so much, guys. Have a good night.